Okay, so here's a problem. Find out which one of these is the oxidizing agent, which one is the reducing agent, what's being oxidized, what's being reduced, what the oxidizing agent is, and what the reducing agent is. All right, let's go over this. Okay, so what we got to do is go through everything and figure out the oxidation states. All right, so we know from those 4 rules that oxygen is always a -2. All right, unless it's elemental state, which it's not, because it's bonded to another atom. So the overall charge on this is a 0, right, because it's a neutral molecule. Therefore, my carbon in this case also has to be a +2. Or not also, it is a +2. Okay. Over here, my oxygen is a -2. Oxygen is always -2, again, once it's elemental. This overall charge is a 0, otherwise I would have a charge here. I'd have like a -1 or something there. So in order to figure out what iodine is, let's come down here. So both my iodines plus all 5 of my oxygens, in this case, have to equal an overall charge of 0. The oxygen, so it's 2 iodines minus 10 equals 0. So 2I equals +10. And then you divide each side by 2 to get iodine equal to a +5. So my iodine has a +5 oxidation. All right, any questions on that? Everybody see how I did that? Everybody good?
Okay. Sorry.
Yep.
What? Never mind.
Okay.
Put it out.
Okay, good. Okay, so now on the other side, I do the same thing. So this oxygen -2. This carbon is going to have a +4. All right, has a +4 because it's carbon. -4 equals 0 because the overall charge up here is 0. If I had a charge up there, I would say what the charge is. I'd have, like a -2 or something there, or something like that. But I don't have a charge, so we assume it's 0. All right. Oh, no, sorry. Right here. So carbon equals +4. And then my I2, this is the elemental state of iodine. Remember, iodine is one of the diatomic molecules, so this has an oxidation of 0. All right, so now I look to see which atoms are changing from side to side. So notice the carbon starts, so that carbon starts as a +2, and it goes to a +4. All right, so I'm becoming more positive. If I look on the scale I gave you, here's 0, I have a +2, and then +4. I'm going this way, I'm going towards the right, I'm becoming more positive. So that means I'm losing electrons, therefore this is being oxidized. So my answer for the oxidation is either C+2, or you can write it as CO. All right, your products are never the answer. Your products can't ever be the answer. So all these answers have to be one of these two. Okay, because this is the outcome of the reaction. The I2 isn't oxidizing. The I2 is the outcome of what happened with the I2O5. So this is doing something, either oxidizing or, in this case, it's reducing. Therefore, this is what I get afterwards. So your answers for all these are always what I'm starting with. Okay, because it's my C with the 2+ charge that is oxidizing, and it's becoming a C+4. Right? This is not oxidizing. This is the outcome of the oxidation. Okay, so if it's oxidized, which agent is it? Either put O or R in the chat. Tell me if it's the oxidizing agent or the reducing agent. Yep, it is the reducing agent. That's correct. Because remember, it's the opposite. Whatever's being oxidized, it is the reducing agent. All right, or again, you can put C+2 if you want. Usually, in this case, we actually put the actual reagent because it's the whole thing. But my oxygens aren't changing. It's really the iodine and the carbon. And then the iodine is starting out as a +5, and it's becoming a 0. So it's starting as a +5 here, and it's moving to the left. It's gaining electrons. Right? It's going from more positive to a lot less positive, so more negative. It's going towards the negative side. So it's gaining the negative, so therefore that's being reduced. So this answer, you can either put I +5, or you can write the actual reagent itself. So if it's being reduced, it is the oxidizing agent. So again, I +5 or I2. Choose which one you want to write as your answer. Don't write them both on exams or anything like that. I guess they're all multiple choice at this point. But if I do have you write stuff out, don't show me both. Just choose one or the other. If you had to choose one of them, choose the actual reagent itself. That's a lot better to actually put this is the thing that's being, in this case, oxidized. This is the thing that's being reduced. Okay? I want to do another one, but I'm going to see if there's any questions.
I have a question.
Sure.
So, on the left side, I see that there's 6 oxygens, and on the right, there's 2. But that doesn't matter in this?
Yeah, because I don't have it balanced. I mean, if you balance the equation, then yeah, it will.
Oh, okay.
It'll work out. Yeah. Yep.
Okay.
All right. Any other questions? All right. Let's do. This is a good one. Put here plus water. Okay. So again, same thing. Show me what is being oxidized. Let's put here oxidized. What's being reduced? What's my oxidizing agent? And what's my reducing agent? Okay. Put it on pause. Excuse me. A bunch of people died. So let's go over it. All right. So starting on the left side, do the oxidation. So chromium. So this goes back to trying to figure out like the charges, just to make sure that all the charges are correct. So again, this goes back to what we learned back in chapter, I can't remember which chapter we did, naming 3. Again, I have a transition metal. Transition metals can have more than one possible oxidation. So I'm doing the reverse crisscross on it. I have a 1 there. So that tells me I have a chromium with 3+, and a hydroxide, which is a polyatomic ion, has a -1 charge. Since that is a -1, this is actually a +3. So this chromium will have a +3. Okay, so don't forget all your rules. I told you yesterday, we still use all the same rules. We haven't really learned that much anything new. The only thing that we've learned new is how to figure out the oxidations of a polyatomic ion. It's really the only thing that we learned new. All the other rules still apply. All right, for hydroxide, we know oxygen always has a -2, and hydrogen has a +1. All right, plus if we look at the hydroxide, if oxygen's -2, my oxygen has to be +1 to give me an overall charge of -1, which I have. All right, and then bromine, since it's Br2, it's the elemental state that has a 0 charge. So coming over here, I have a polyatomic ion. This is the new thing that we learned. So chromium plus my 4 oxygen. So oxygen again is a -2. So this is a -8 equals -2. So my chromium in this case will have a +6 charge. All right. Bromine has a -1. That's pretty easy. That's all it is. It's -1. Hydrogen is a +1 and oxygen is a -2. Change colors again. So my chromium is going from a 3 plus to a 6 plus. So you guys tell me, is that oxidation or reduction? Just put an O or an R. Oxidation, very good. Good, guys. Yep, Kimberly, Justin, very good. Oxidation. I'm getting less negative, more positive. So the chromium 3 is being oxidized. So I'm going to put here as my answer, CrOH3. All right. So if it's oxidized, which agent is it? Is it the OA or is it the RA? The RA. Good. You guys got it. And then therefore the bromine is going from a 0 to a -1. So Br2. So these equations I'm writing down here are what's called the half reactions. I think they're very helpful so that you can actually see everything very clearly. It just shows what that particular species is doing. It kind of ignores everything else and just clearly shows you 0 to a -1. So this is clearly gaining electrons. So Br2, and my oxidizing agent is Br2. Okay? So again, these in your book are called half reactions. I think it just it takes all the clutter, so it just focuses on this, and it just shows me what it's doing. It ignores everything else. Kind of takes all the clutter out. Okay? You guys good? You guys want to do another, or do you guys think you have it? What do you guys want to do? You're good, right? Kayla's good. Anybody else? I mean, if there's one person that wants to do another one, we will do another one. But if everybody's good, then we can just move on. Okay. You guys are good? Everyone got this? I'm going to hit clear. Okay. So the last thing I want to talk about in this chapter is reactions where gas is formed in the reaction. All right, up until now, the reactions we've talked about. So let me actually do a summary again of the reactions that we've talked about. Let me go back to here. I like using this better for writing. So there have been two major types of reactions. The first one is a double replacement. All right, and the two reactions we talked about was a precipitation reaction, and the second one was the acid-base neutralization. Okay, so that's what we talked about mostly last week and a little bit on this week. And then the second type of reaction we've been talking about the past 2 days is redox reactions. Okay, and there are 4 types. There's a combination, there's a decomposition, which is the opposite of the combination. There is a single replacement, which we talked about yesterday, how batteries work. And then finally, the fourth one is a combustion reaction. And we talked about how you determine what's being oxidized, what's being reduced, what the oxidizing agent is, and what the reducing agent is. All right. And then a third type of reaction, which is kind of a type of a double replacement reaction, it kind of fits in this category, is one where you form gas production. All right, so in this case, I form a precipitate, I form a solid. In this case, remember, we always form liquid water, so water's formed as a liquid. But we're going to talk about a third type, which really fits under here, but not always. It could also fit under redox, but we're going to look at it more as an acid-base type of reaction, is where it's gas production. So let's just look at the example that they have. So notice they have hydrochloric acid, and you're adding it to a carbonate. So mostly gas, you know what, I'm going to copy this and paste it over to the, over here. I'll make that really big. It's You guys can see it. I got to get my chat thing out of the way. Okay, so these reactions, anytime that you have gas formation, it's usually a carbonate. So we're usually talking about the molecule either has a carbonate on it or a bicarbonate. These are the ones that we're going to talk about in our class, but there are other types. But these are the main types. So it either has a carbonate ion. Remember, carbonate is CO3 with a 2- charge. Bicarbonate is HCO3 with a minus charge. Okay. So one of your starting materials is going to have one of these compounds on it. So notice here I have a carbonate ion. Right here I actually have carbonic acid as a molecule, which I'll talk about in a second. Okay, so what happens? So I'll give you a perfect example, like baking soda. Right? Baking soda, the formula is it's sodium bicarbonate. That's the formula for baking soda. Sodium. So if you have baking soda in your house, you can look on the back of it. It's a sodium bicarbonate. Actually, since you guys are at home, and if you want to do an experiment at home, take sodium bicarbonate or baking soda and add it to vinegar. Some of you might have done this. It's like the volcano reaction. So if you do it and you add it in there, it fizzes and it foams and all that stuff. I'll tell you what, guys. I will tell you what. I'm going to do a demo for you guys. How sweet is this? I'm going to do a demo for you. I'm going to do this. I have it all right here. So give me 1 second. I'm going to get everything. Yes, it's right. And I can still do demos. I got all this stuff at home. So just give me 1 second. I'll get it all and I'll bring it. I'll probably have my kids all come over too, because I'm sure they'll want to watch it. So just give me 1 second. Oh, uh-oh. I just closed that window. Okay, here is baking. I don't know if you guys are able to see it. Oh, there's a white powder. Everyone knows what baking soda is. So hold it up so that everyone is able to see it in there. Yep, okay. I saw Kimberly says yep. See that? The students are talking to me through the chat.
Do they have mics?
They do. Can you make yourself full screen? Yes, I think I have to stop sharing. Isn't that correct? That's probably what I got to do. Does that help? Yep, okay, good. All right, good. You guys can see full screen, we can't. All right, you want to see the baking powder? All right, I'm sorry, the baking soda. Baking soda. I'm going to pour water in there just so it dissolves. Okay. Am I getting on there? So I'll try to dissolve as much as I can. So what state right now would you guys say that the sodium bicarbonate is in? So is it a liquid state, solid state, gas state, or aqueous? Aqueous, very good. You see everyone says aqueous? Do you know what aqueous means?
Is it like you just told me, isn't it like a powder and a liquid kind of
So
combined?
it like all dissolves in the water. You take it and dissolves in water.
Does it harden?
No, it's all dissolved in
like
there.
Okay.
Yeah, it's hard to tell right now.
Chemistry.
I'm sure they're cracking up at that. All right, so it's not. I mean, I have a lot in there, so it can't be all dissolved that much. But so actually, here's a good example of a saturated solution. All right, guys. So I have a lot dissolved in there. All right, so keep holding that. Let me see if I can. I think maybe this is make this a little darker.
Ah, that's better.
Is that easier to see for you guys?
They're saying yeah.
Okay, good. All right, here I have vinegar. Much better. Okay, good. I have vinegar. I'm going to drop it in there. All right, hold it up so I can see. You're doing a great job. Perfect. There we go. All right, now I'm going to add a lot of it because I don't want the fizz completely up, but I'm going to try to add just very slowly. Why don't you hold it closer so the mic is right there? You able to do it? Okay. Okay, ready? Hold it down just a little bit. Okay, ready? Here we go.
Ah!
Do you guys see the fizzing? Oh, there it goes. Now you guys saw that.
Yeah, a little bit more.
Whoa! All right.
Cool.
You guys see? Isn't that cool? All right, let's see. Yeah, very fun. I know, right? There you go. And then eventually, so I don't know if you guys can see, but a bunch of little bubbles are coming up from the bottom. There's a pile of it at the bottom. All right, see it all fizzing? Mentos and Coke, that's right. Well, that's interesting because that's not actually a chemical reaction on the Mentos and Coke.
Really? I thought it was.
We can talk about. So what happens with that is that on the Mentos have a lot of surface area on it. When it goes into the Coke, all of the CO2 is able to actually form into a gas immediately on the surface of the Mentos. So it's not a chemical reaction. It's actually a physical phenomenon. All right, so there we go. Might be hard to. So if you guys have baking soda or whatever vinegar, kind of a demo I do. I've actually done it for your class. Is I'll take like a 1 liter bottle of soda or something, and I'll put in like the vinegar in here, and I'll put the baking soda in a balloon.
Oh yeah,
and
then
then
it like rises up.
Right, and I put the balloon on top of here, and then I dump it over, and all of the bicarbonate will go in there. It turns into a gas, and the balloon blows up. Yeah.
It doesn't blow up fully. It just kind of expands.
Expands. Right. Perfect. All right. So there we go. Thank you very much, Zach.
Yeah. Bye.
All right. Kimberly says thanks, Zach. All right. Let me go clean this up real quick. I'll be back in 1 second. Yeah, virtual lab is so easy. That's right. Oh, thank you guys for. Oh God, Holly, that's so funny you said that. My son said, "I wonder if they saw my shirt." But yes, his shirt says, "I'm powered by bacon." That's correct. It's his favorite shirt. Yeah, it's kind of funny. Actually, a few months ago, so we're Jewish, and he went to Hebrew school, and he wore that shirt. And the rabbi was like, "Yeah, you probably shouldn't wear that shirt into here again." So it was, he didn't. Yeah, isn't that funny? Yeah, she's like, "It's not very kosher." He's like, "Well, I'm not eating bacon. I'm just wearing the shirt." So that was kind of a funny thing. All right, so let's go back to the actual chemistry. Yeah, isn't that funny? Yeah. So now, actually, once I was like right before that we had to stay home. He actually had it on. I said, "Zach, you probably shouldn't wear that shirt. You better take that off." So okay, so that's the bicarbonate. So what vinegar is? Hold on 1 second. Vinegar is HC2H3O2. Okay, which is acetic acid. So the reaction is you have your sodium bicarbonate plus acetic acid, HC2H3O2. Okay? And what happens is you have a double replacement reaction. So if I write this out in the ionic form, so I'm going to do this, in a complete ionic. You have a sodium ion, and then you have the bicarbonate ion. Remember, if you look on the polyatomic chart sheet, you have that as a bicarbonate. And then you have your vinegar, which is an acid. Remember, acids are H pluses, plus you have your anion. Okay, so here's the complete ionic equation. So what happens is a double replacement. Your sodium pairs up with the acetate ion to form sodium acetate. I was going to go over this, I forgot to show you, but this stays aqueous, right? So if you remember, if you look on the solubility chart, anything that has a sodium on it is aqueous. I think also if it says acetate, it's aqueous too. All right, and then your other product, let me do it in a different color just so it doesn't blend in. Actually, why don't we just erase this over here?
What chart says what's aqueous and what's not?
It's the solubility chart that we went over. I think it was last Wednesday, where you look. I can probably let's see. Actually, it's probably on these slides. It was the last chapter. Oh no, it's right there. It's that chart.
Okay, I have that.
Yeah.
How do you tell if it's aqueous or not?
So why don't you go back and look at the videos I did on that, because I talked about that already. Yeah, I went over all that. All right, and then, so we can go back to the blue. If we have time after class, Kimberly, I can go over it again.
Okay, yeah, I mean, if you say it already, I can just go back.
Yeah. And then, in this case, your hydrogen is going to pair up with your bicarbonate to form H2CO3. Okay? And H2CO3 is what's called carbonic acid. And carbonic acid is not stable in water. Under pressure, it's very stable. So, like in soda, when it's pressurized, it's stable. That's what the pressure is. It's all of the CO2 in water. But once you open it, carbonic acid breaks down very quickly and easily into CO2 and water. All right, and CO2 obviously is a gas, and water is a liquid. So when I took the vinegar and I added it in the baking soda, all that gas, all the fizzing is of the CO2, because what we're forming is the carbonic acid, which is then immediately breaking down into CO2 and water. All right, and you can kind of see it up here. You see how they have the H2CO3? That breaks down very easily into water and CO2. Also, if you look at this reaction up here, if you take sodium carbonate and hydrochloric acid, it does the same thing. Your sodium pairs up with the chlorine to form the sodium chloride, and then your hydrogen pairs up with the carbonate to form carbonic acid, which again breaks down into H2O and CO2. Okay? So anytime you see carbonate or bicarbonate and you're mixing it with an acid, you have to remember that if you form carbonic acid, you don't actually write carbonic acid. So my actual answer here should be NaC2H3O2 plus CO2 plus H2O, because these are the carbonic acid, but carbonic acid does not really exist in our regular pressure environment. It has to be pressurized. Okay? Does that make sense? So, let me see if I have a... So if we do something here, I'm going to clear this. Does everybody have that? I'm going to clear this. So let's say we take sulfuric no, not sulfuric acid. Oh, yeah. Actually, I'm going to take phosphoric acid and add it to, let's say, potassium carbonate. All right, show me what the products are. Actually, in this case, what I want you to do, because this is a double replacement reaction. So this is aqueous, and this is aqueous. Do a complete ionic equation for everything, and do a net ionic equation. Okay. So this is technically also a type of a neutralization reaction, because carbonates are a base. I think back in the chat, I think I asked you guys about like something, and I think that Kimberly said it's a base. And you are right, it is a base, but for that question, I don't think I wanted the base as the answer. But you did say base somewhere, and I can't remember where it was. Yeah, there it is, base. Is that from Justin or Kimberly? I can't remember if that's from Justin. I can't tell. I don't know if the names are on top or bottom. That was Kim. Okay. So these carbonates are a type of base. They are used to actually neutralize acids. So usually, if you have an acid spill, you usually add a carbonate on top of it in order to neutralize it. And this is the equation that happens. Okay, so I'll give you some time, work on that problem. And again, in the box, let me know when you guys are ready. All right, Jack. All right, let's go ahead and do this. So you've got phosphoric acid, which breaks down into H+ ions and phosphate ions. Now, if you want to balance it, you can go ahead and balance it. So that means you have to put a 3 here. So, you know, if you're wondering where this 3 is, it's still there. It's just I'm making 3 H+ ions. All right, don't put the 3 here because that is not a correct ion. All right. And then the K2CO3, you have potassium ion, and you have a carbonate ion. So those are ions. And again, if you want to put a 2 here, it's totally fine. But I don't care too much about the balancing of these equations. I care more about the balancing of the net ionic equation. So your H is going to pair up with your CO3, and it's going to form H2CO3, which again is the carbonic acid. But you're going to write it as water, and water is a liquid, which we learned about the last time, and CO2 is a gas. And then you form the K2PO4, K3PO4, and that is aqueous based off of the solubility chart. Because anything that has a potassium is always soluble. So if we do the complete ionic equation, whatever is aqueous stays as ions. So that will stay as a K+ and a PO4 3-. And then if it's in any other state other than aqueous, you actually write the whole entire molecule. So H2O is a liquid, it's not aqueous anymore, and CO2 is a gas. So that would be your your complete ionic equation. So H2O, CO2, potassium ions, and phosphate ions. So again, anything that's still aqueous, you write in the ionic form. Anything that is not aqueous now, if it's a solid also, you write it as the actual formula. Then cancel out the spectator ions, which are the ions that are the same on both sides. In this case, it's a phosphate, and a phosphate, and a phosphate, and a potassium, and a potassium. And whatever is left over is my net ionic equation. So that would be H+ plus CO3, 2-, gives me H2O plus CO2. And to balance it, you'd have to put a 2 right there. So this is my net ionic equation. So if you look, it's basically a neutralization reaction. You have acid plus carbonate gives you water and CO2. So it neutralized. Okay, so any questions on that? Does that make sense? All right, good, Kayla, thank you. Okay, so that's the last reaction, which it's the one that forms a gas, which is our CO2 in this case. and it kind of, like I said, it fits under the double replacement neutralization reaction. Okay. Okay. And I believe that is it for the chapter. So let's see the gas. Yeah, here's an example in this book where they talk about all these sulfur compounds form SO2. I'm not going to go over that. You don't have to know that, but it's just another ion that forms a gas. We just basically talked about all of the carbonates, but you can also do it with these this bisulfite ion as well. It forms H2SO3, and H2SO3 right here. H2SO3 breaks down into H2O and SO2. Very similar to the carbonates, but in this case, it's the sulfites. But like I said, we're not going to worry too much about it. And then section 6 is basically a review to try to figure out what type of reaction you're doing. If it forms a precipitate, is it a precipitation reaction? If it doesn't, is there an acid in there and you form water to acid base? If not, then it has to be a redox reaction. This is just kind of a slide just to kind of show you how to figure out a type of reaction it is. So I'll let you guys kind of look at these on your own. But I think pretty much it sounds like you guys have a pretty good handle on it. Again, the way that you know the difference between a double replacement and a redox is if the charges change or the oxidations change on each side of the equation, then it'll be a redox. Notice in this reaction, the hydrogen is a +1 charge, all right, and it's ending up as a +1 charge. The oxygens here are -2s. The oxygens here are -2s. The potassium is a +1. Potassium is a +1. All right. Our carbon here is a +4. Our carbon here is also still a +4. The phosphate here looks like it's a +5, and it's still a phosphate over here. It's still a +5. So none of the charges are changing, so it can't be a redox. Okay. Remember, a redox is where you have something that loses electrons and something gains electrons. Here, nothing is losing or gaining. They're just changing the ions on each other. So this is not a redox. All right, but if you have something where you have a zinc plus HCl and you form H2 and zinc chloride, okay, this is a redox because zinc is starting at 0 and it's becoming a +2. Your hydrogen's a +1. Over here, your hydrogen's a 0. Your chlorine is -1 and the N still is -1, so that's the spectator ion, but I'm changing oxidations here, so this is a redox. This is a double replacement. Okay, so that's kind of how you know the difference between the two. All right, any questions? Yes. No questions? All right. All right, I kind of want to start just a little bit, chapter 11. We don't have to do the whole thing. Also, remember that we have the problems. So these practice sheets. All right, in class, what we would normally do is in class I would hand this out and you guys would work on them in class, but since you guys are able to do this on your own, so just remind you, you guys should. So here's some practice problems. What we'll do tomorrow, because tomorrow is Thursday. Thursdays we usually do kind of a review and we do some problems. I'll bring some more problems, but or we'll do a few of these problems on the sheet. So there is some balancing. Here is writing a complete net ionic equation. And then here we have a bunch of equations where you draw the product, the complete ionic and the net ionic, and balance them. Here is all determining oxidation numbers. And then here is like the problems that we did like today. Assign what's being oxidized, what's being reduced, what's the oxidizing agent, what's the reducing agent. And then here is looking at the reactions in 8 and trying to figure out, is it decomposition, combination, single replacement, a double displacement, or a combustion. So it should tie everything all together and have a bunch of problems. Write the balance equation for the combustion of these. And then write a chemical equation to represent the sublimation of CO2. Is it exothermic or endothermic? So that's the practice sheet. All right. Did I download 10 yet? Okay. So let's get chapter 11 and start with that. If you haven't watched the videos yet, watch the videos. But are there any questions before I do this? I'd rather answer the questions in chapter 10. I think what we'll do is I'll probably just go maybe for 10 minutes, and then we'll end class there. I don't want to get too far in 11, just because it's not on the exam. I want to focus more on 8, 9, and 10, but I feel like I have to get a little bit of it done, just so that we stay on schedule. And then, Kimberly, if you wanted to, after class, you can stay, and I can go over that solubility chart. And if there's anybody else that wants to go over it again, I'm more than happy to do that. Okay, yep, no problem. Okay, so this chapter, using balanced chemical equations. So this chapter is about, let me kind of tell you what the reasoning about this. This is, let's say you are a chemical company and you want to make a certain compound. All right, let's say that you want to make aspirin, okay? And you have to make a certain amount of it. Let's say you want to make, a ton of it, or whatever, a lot of it. You don't just randomly add stuff all together and make it. You have to calculate how much of this compound and how much of this compound and how much of this compound. Like, how much of these compounds do I need in order to make a ton of this compound? I don't just randomly add stuff. And on top of it, it's not equal amounts. It's not like I need exactly a ton of compound A and a ton of compound B. It's all based on how many moles I'm using. So I don't want to waste any of the material because it's wasting all the material. Plus, that would cost a lot of money. Obviously, if I'm in business in order to make money, I don't want to waste any money. So I need to calculate exactly how much of each how much of each of the molecules I need in order to make a certain amount of the compound. And that's kind of what this chapter is about. It's trying to do calculations. If I use 8 grams of compound A and 12 grams of compound B, how much product am I able to make out of that? Okay, so we're going to be doing mole-to-mole conversions again, mass-to-mass conversions. We're also going to be talking about what's called a limiting reagent. So if I have like 8 grams of one compound and 1,000 grams of another one, obviously that 1,000 grams, I'm not going to use all of it. I'm only going to use a certain amount of it. So the compound where I used 8 grams limits the amount of compound of the 1,000 grams I'm using. All right. So that's basically what this chapter is about. It's about doing these calculations. So and the fancy word for this is called stoichiometry. Okay, so stoichiometry is the fancy word for basically doing balanced equation math problems in chemistry. All right, so their way of defining it refers to the numerical relationship between the amounts of reactants and products in a balanced equation. All right, I like mine better. It summarizes it better. But basically, we have a balanced equation, so it means I have 2 moles of CO react with 1 mole of O2 to make 2 moles of CO2. Okay, so we're going to be talking about new types of mole-to-mole conversions. So if you remember from last exam and stuff, we had the mole-to-mole conversion saying for every 1 mole of H2O, there are 2 moles of hydrogen. right? For every 1 mole of H2O, we have 1 mole of oxygen. Okay, that was last exam, right? It's saying for this whole entire thing, how many moles of each atom are there? Well, in the balanced equation, it's a little different. It's basically saying for every 2 moles of this reactant, I need 1 mole of O2. So 2 moles of CO is equal to 1 mole of O2. Again, it's 1 because I have an imaginary 1 in front of that O2. Or you can say something like 1 mole of O2 produces 2 moles of CO2. So I'm comparing my O2 versus my CO2. It's one of these makes twice the amount of those. And then the last mole-to-mole conversion is 2 moles of CO make 2 moles of CO2. Okay? So this is a new way of doing mole-to-mole conversions. It's the same thing. It's all comparing one thing versus the other thing, and I'm using the balanced equation in order to figure it out. Okay, if you remember the rocket lab, all right, we did the rocket lab. We did this in the rocket lab without you guys even realizing that we were doing this. Okay, because we said that it was a 2-to-1 ratio of hydrogen and oxygen, right? I think we found out that you needed what was it, 4 parts of hydrogen versus 2 parts of oxygen, right? Which is basically a 2-to-1. Okay, well, that's what we're doing, the mole-to-mole conversions. Twice the many moles of hydrogen for every 1 mole of oxygen. Okay. So let's see, calculate the amount of urea that will be produced by a complete reaction of 5.25 moles of ammonia. Okay, so here is an example. So why don't we do this problem? Let me see if I can copy and paste this. Because the best way you learn how to do this is by doing problems. I don't know why it keeps going so big. I should get the balanced equation too. There we go. Shows no 2. Okay, so calculate the amount of urea. That's great. You know what? Hold on a second. Give me a second. I think this program is better. I think I told you guys about Jing, right? If you guys don't have it, you should get it. It's really helpful for stuff. So this equation is saying calculate the amount of urea. This is urea right there. Okay, can be produced by the reaction of 5.25 moles of ammonia. So I'm starting with 5.25 moles of that. So I'll do the problem here. So it's saying I'm starting. Okay. So I'm starting with 5.25 moles of ammonia. So 5.25 moles of ammonia. Okay, right there. And I want to find out, calculate the amount of urea. I assume they imply grams there. Anytime they say the amount, we're going to talk about grams of urea. Okay? So what I got to do is so I'm already in moles of ammonia. I have to convert it to moles of urea. This is a mole-to-mole conversion. Remember, anytime I give you information about one compound, and I want you to give me an answer about another compound, we got to use a mole-to-mole conversion. So in this case, I'm going to use the balanced equation. So there are 2 moles of ammonia for every, remember I have a 1 here, 1 mole of urea, NH2CO. Does that make sense? Everybody understand that? How I'm getting this 1 to 2. And then I multiply it by the mass of urea. 1 mole of urea. I'll just put the word urea. Now I got to calculate how much urea is. So it's 14, it's 28, plus 4, plus 12, plus 16. I get 60 grams of urea. Okay, so everybody understand what I'm doing here? So I give you information of this. So I'm saying if I have 5.25 moles of this, so if I do this reaction and I'm starting with 5.25 moles of this, how much of this can I possibly make from that? So do the math. Let's see. You should get 157.5 grams. Technically 3 sig fig, so 158 grams. Okay? So that's basically how this works. You know, if I give you a balance, so first thing is check and make sure that the equation is balanced. It was already balanced for me. If it's not balanced, you got to make sure you balance it. And you know on the exam that I'm going to do this is part of it is balancing the equations. So you might have to balance the equation and then also do the problem as well. Notice I don't care about like CO2 or water because they aren't part of my problem. So I don't have to use any of that information. It's just strictly talking about if I use, you know, this amount of ammonia, how much urea can I possibly make out of that? Okay, and then if you look through it, they wanted it in moles, but I did it in grams. All right, here's one of these charts. You guys remember these charts that we did for the last exam? I think it's kind of helpful. It's the same thing, moles to grams or stuff like that. So here's a problem. Laughing gas commonly used. Okay, so let's do this one. I'm going to copy this and paste it in there. And this will be kind of the last thing that we'll do. Okay, so nitrous oxide, NO2, is also known as laughing gas, is commonly used as anesthesia in dentistry, is manufactured by heating ammonium nitrate in the balanced equation. So calculate the mass of ammonium nitrate that must be heated in order to produce 10 grams. I'm going to actually change this into water. So change this to water. Okay, actually, you know what? Just erase all that. So calculate the mass. So how much of this do I need in order to make 10 grams of this? That's basically what the question is on. Determine the core. Oh, I have it as part B. Never mind. It's part B. Okay. So I'll tell you what. I'll give you guys about 3 minutes to do this. I'll give you the masses of everything just so I can speed it up. So 28. So ammonium nitrate is 83 grams per mole, and water is 18, and this one is 44. Okay, so I'll give you about 3 minutes to do that, and when we come back, I'll go over that. Okay, so let's go over this. So I'm trying to calculate how much of the ammonium nitrate I need if I'm starting off with 10 grams of water. So I'm starting with 10 grams of water. And remember, my final answer has to be grams of ammonium nitrate. So if you remember this chart, grams of A to moles of A. And then we did that mole-to-mole conversion to moles of B to grams of B. Okay, so I got to first convert to moles of water. So I'm going to divide it by 18. Now I got to do the mole-to-mole conversion. So there's 2 moles of water for every 1 mole of ammonium nitrate. Now I need to find the mass, so I just went from A to B. Now I got to find the mass of B using the molecular weight of the ammonium nitrate. Ammonium nitrate, what did I say, 83 grams. And that should give you the answer. So, uh, 23, does that sound right? Let's do 3 sig figs, so 23.1 grams. Does that sound right with everybody? Just say a Y or a no. Yep, okay, good. Good, Holly. That's basically how this chapter works, or how these equation works, and it's all sorts of combinations of this, which I'll go over all the possible types of problems. So that's basically it. Same type of stuff we learned previously, but this time this is the new part. The mole-to-mole conversion comes from a balanced equation. Notice I didn't need to use any of this. I gave you the mass just to give it to you, but you didn't need it in this problem because the problem isn't asking for that. I mean, it did in part A, it did. All right, and if you did that, it would just be a 1-to-1. That's why I didn't do it, because a 1-to-1's boring. If you forgot to do this, you'd still get the same answer, even if you didn't do the mole-to-mole conversion, since it's a 1-to-1. But I wanted to make sure that you know about this thing. This is the important part of this, that you understand how to do that from the balanced equation. Okay? Any questions?